James Webb, once again, is pushing the limit of what we can see. Back in 2020, NASA's Chandra X-ray Observatory made history by announcing the most energetic, explosive event ever discovered in the universe. In a galaxy cluster, some 390 million light-years away, a supermassive black hole emitted a jet that created an enormous cavity in the intergalactic space of that galaxy cluster. The total amount of energy required to create this observed phenomenon? 5 multiplied by 10 to the power of 54 joules. More energy to occur in any singular event ever seen since humanity first began studying the universe. Only the Big Bang itself, which contains all of the energy within the entire universe by definition, was more energetic. But there's another class of event that definitely exists in the universe that can output even more energy in a shorter amount of time. The merger of two supermassive black holes. Logically, these giant black holes, each millions to billions of times heavier than our Sun, must collide and merge too. Such mergers can channel huge volumes of material into the black holes, sparking violent astrophysical outbursts that shape star formation and other processes in their host galaxies. And now, such a powerful event has just been captured by James Webb. Thanks to its infrared eyes, we have found the most distant merger between supermassive black holes ever detected, shedding new light on the growth of black holes in the early universe. What's more, these cosmic monsters have been detected at the dawn of time, further challenging leading theories of cosmology. Join us in today's episode as we dig deep into how the latest result from James Webb just upended our understanding of the universe. There are lots of events that can be considered either explosions or cataclysms in the natural universe, where a large amount of energy is released over a short period of time. A very massive star that reaches the end of its life will explode in a cataclysmic Type II supernova, creating either a black hole or neutron star as a stellar corpse. Over the final few seconds of its life, it will release some 10 to the power of 44 joules of energy, with hypernovae or superluminous supernovae reaching up to or even over 100 times that typical amount. For a long time, supernovae were used as the standard by which all other cataclysms were measured. As the brightest electromagnetic events in the sky, they could outshine entire galaxies, dependent on their individual brightnesses and the overall mass of the galaxy in question. The only things that rivaled or exceeded the energy released in a supernova were gamma-ray bursts or larger scale, extended events such as merging galaxies or galaxy clusters, or supermassive black holes feeding on enormous amounts of matter. During the 2010s, we uncovered the origin of at least some gamma-ray bursts, colonovae, or the merging of two neutron stars. Between gravitational waves and electromagnetic radiation, a significant amount of mass, about 10 to the power of 29 kilograms worth, or around 5% of a solar mass, gets converted into pure energy, leading to an energy release of about 10 to the power of 46 joules. On the other extreme, active galaxies and quasars can be even more energetic. Enormous amounts of mass, perhaps millions or even billions of solar masses worth, can get funneled into a central, supermassive black hole where it gets torn apart, accreted, and accelerated. The matter and radiation emitted can reach a total of 10 to the power of 54 joules of energy, although it's emitted over about 1 million years or more in time, making it a high-energy but low-power event. But the universe gives us a way to emit even larger amounts of energy, and to do so on much shorter timescales. The key to unlocking this came last decade, when the NSF's Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the first gravitational wave event from two merging black holes. For the very first one ever seen, two black holes of two different masses, 36 and 29 suns worth respectively, merged together to produce a final state black hole of a lesser mass, just 62 suns worth. This was an enormously big deal, netting a number of scientists the 2017 Nobel Prize for the discovery of gravitational waves. Over the subsequent years, many more black hole mergers and merger candidates have been detected, with approximately 100 known so far to date, and many more are expected in the new and upcoming runs of LIGO, Virgo, and Cagra, humanity's greatest gravitational wave detector array. In all cases, the same bizarre and fascinating behavior has been observed. Large amounts of mass are converted into pure energy over a timescale of just a few milliseconds, or the final moments of the inspiral and merger of black holes. In particular, 2 points are extremely interesting about these black hole mergers. First, in all cases, the peak power that was emitted, or energy per time, was about the same. They all outshone all the stars in the universe, combined for a tiny fraction of a second, but the more massive mergers had their peak power output occur over longer periods of time, emitting more total energy. Second, you can make a very simple approximation for the total amount of energy released in gravitational waves in a black hole merger. About 10% of the mass of the lower mass black hole gets converted into pure energy via Einstein's E equals mc squared. Although extremely lopsided mass ratios can bias this figure to somewhat lower values, about 10% remains an excellent approximation for all black hole mergers ever observed as of 2023. For the first black hole merger ever discovered, the total amount of energy emitted was $10 to the power of 48 joules, and that occurred over a time interval that spanned just 200 milliseconds or so, leading to a fascinating possibility. Instead of two stellar mass black holes merging together, where the masses of each black hole range from a few to a few dozen solar masses, we could look to the most massive black holes in the universe, the supermassive ones found at the centers of galaxies. When they merge together, a series of events will unfold, resulting in the largest release of energy that, at least theoretically, should ever occur in our post-Big Bang universe. And what's interesting, such a terrifying event has just been captured by James Webb. Specifically, a new stunning observation with NASA's time machine has found the most distant merger between supermassive black holes ever detected. The colliding black holes are at the heart of merging galaxies that are so distant that the collision is seen as it was happening just 740 million years after the Big Bang, when the 13.8 billion-year-old universe was a fraction of its current age. Astronomers have long suspected that supermassive black holes with masses millions or even billions of times that of the Sun, which are found at the heart of most large galaxies, have been responsible for driving cosmic evolution. This new James Webb finding indicates that supermassive black holes have been in the driving seat almost since the beginning of time. On the other hand, the observatory has been regularly uncovering supermassive black holes in the infant universe, which has been a problem because the merger process that facilitates their growth should take periods in excess of 1 billion years. These results could also help solve the troubling mystery of how supermassive black holes grew to tremendous masses so early in the history of the universe. As research leader and University of Cambridge scientist Hannah Ubler said in a statement, "Our findings suggest that merging is an important route through which black holes can rapidly grow, even at cosmic dawn." Together with other Webb findings of active, massive black holes in the distant universe, our results also show that massive black holes have been shaping the evolution of galaxies from the very beginning. Imagine the universe in its infancy. Most scientists think space and time originated with the Big Bang. From that hot and dense start, the cosmos expanded and cooled, but it took a while for stars and galaxies to start dotting the sky. It was not until about 380,000 years after the Big Bang that atoms could hold together and fill the universe with mostly hydrogen gas. When the cosmos was a few 100 million years old, this gas coalesced into the earliest stars, which formed in clusters that clumped together into galaxies. the oldest of which appeared 400 million years after the universe was born. To their surprise, scientists have found that another class of astronomical objects began to appear at this point too: quasars. Quasars are extremely bright objects powered by gas falling onto supermassive black holes. They are some of the most luminous things in the universe, visible out to the farthest reaches of space. The most distant quasars are also the most ancient, and the oldest among them pose a mystery. To be visible at such incredible distances, these quasars must be fueled by black holes containing about 1 billion times the mass of the Sun. But conventional theories of black hole formation and growth suggest that a black hole big enough to power these quasars could not have formed in less than 1 billion years. However, in 2001, with the Sloan Digital Sky Survey, astronomers began finding quasars that dated back earlier. The oldest and most distant quasar known, which was announced in January 2021, existed just 670 million years after the Big Bang. In other words, it does not seem that there had been enough time in the history of the universe for quasars like this one to form. Many astronomers think that the first black holes, seed black holes, are the remnants of the first stars, or known as population 3 stars, which we think formed when primordial gas cooled and fragmented about 200 million years after the Big Bang. Population 3 stars were probably more massive than stars born in the later universe, which means they could have left behind black holes as hefty as several hundred solar masses. These stars also probably formed in dense clusters, so it is likely that the black holes created on their deaths would have merged, giving rise to black holes of several thousand solar masses. However, even black holes this large are far smaller than the masses needed to power the ancient quasars. Theories also suggest that so-called primordial black holes could have arisen even earlier in cosmic history, when space-time may have been expanding exponentially in a process called inflation. Primordial black holes could have coalesced from tiny fluctuations in the density of the universe and then grown as the universe expanded. But these seeds would weigh only between 10 and 100 solar masses, presenting the same problem as population 3 remnants. As an explanation for the first quasars, each of these pathways for the formation of black hole seeds has the same problem. The seeds would have to grow extraordinarily quickly within the first billion years of cosmic history to create the earliest quasars. And what we know about the growth of black holes tells us that this scenario is highly unlikely. Our current understanding of physics suggests that there is an optimal feeding rate, known as the Eddington rate, at which black holes gain mass most efficiently. A black hole feeding at the Eddington rate would grow exponentially, doubling in mass every 10 to the power of 7 years or so. To grow to 10 to the power of 9 solar masses, a black hole seed of 10 solar masses would have to gobble stars and gas unimpeded at the Eddington rate for 1 billion years. It is hard to explain how an entire population of black holes could continuously feed so efficiently. In effect, if the first quasars grew from population 3 black hole seeds, they would have had to eat faster than the Eddington rate. Surpassing that rate is theoretically possible under special circumstances in dense, gas-rich environments, and these conditions may have been available in the early universe, but they would not have been common, and they would have been short-lived. Furthermore, exceptionally fast growth can actually cause choking, where the radiation emitted during these super Eddington episodes could disrupt and even stop the flow of mass onto the black hole, halting its growth. Given these restrictions, it seems that extreme feasting could account for a few freak quasars, but it cannot explain the existence of the entire detected population unless our current understanding of the Eddington rate and black hole feeding process is wrong. As such, a group of scientists has proposed a way that seed black holes massive enough to explain the first quasars could have formed without the birth and death of stars. Instead, these black hole seeds would have formed directly from gas. We call them direct collapse black holes. In the right environments, Direct collapse black holes could have been born at 10 to the power of 4 or 10 to the power of 5 solar masses within a few 100 million years after the Big Bang. With this head start, they could have easily grown to 10 to the power of 9 or 10 to the power of 10 solar masses, thereby producing the ancient quasars that have puzzled astronomers for nearly 2 decades. The question is whether this scenario actually happened. Luckily, the James Webb Space Telescope could be able to find out. The most distant quasars takes the extremely powerful and sensitive infrared eye of James Webb. And most recently, in an effort to investigate merging quasars in the early universe, researchers zoomed in on a galactic system around 12 billion light-years away called ZS7 with James Webb's near-infrared spectrograph instrument. There, they found evidence for very dense gas with fast motions in the vicinity of the black hole, as well as hot and highly ionized gas illuminated by the energetic radiation, typically produced by black holes in their accretion-feeding episodes. What's more, thanks to the unprecedented sharpness of its imaging capabilities, James Webb also allowed the research team to spatially separate the 2 black holes. The team then determined that one of the supermassive black holes involved in this merger had a mass equivalent to around 50 million suns, while they suspect that the second supermassive black hole has a similar mass. The scientists couldn't conclusively confirm this because of dense gas surrounding it. In the words of team member Pablo G. Perez Gonzalez, a scientist from the Centro de Astrobiología, the stellar mass of the system we studied is similar to that of our neighbor, the Large Magellanic Cloud. We can try to imagine how the evolution of merging galaxies could be affected if each galaxy had one supermassive black hole as large or larger than the one we have in the Milky Way. When the 2 supermassive black holes eventually merged, they would have set the very fabric of space ringing with tiny ripples called gravitational waves. These will radiate outward from the collision at the speed of light and could possibly be detected by the next generation of gravitational wave detectors. This could include the first space-based system, the Laser Interferometer Space Antenna, LISA, an arrangement of 3 spacecraft being developed by NASA and the European Space Agency and set to launch in 2035. As the European Space Agency's lead project scientist for LISA, Nora Letzgendorf, said, "The JWST's results are telling us that lighter systems detectable by LISA should be far more frequent than previously assumed. It will most likely make us adjust our models for LISA rates in this mass range. This is just the tip of the iceberg." Even before the launch of LISA, James Webb will continue to investigate early supermassive black holes. Starting this summer, a program in the $10 billion telescope's Cycle 3 operations will examine the relationship between massive black holes and their host galaxies in the first billion years after the Big Bang. This will include searching for and characterizing mergers. This could tell scientists at what rate supermassive black holes collide, and if this is sufficient to explain their rapid growth in the early cosmos. In addition, another fascinating study suggested that the loneliest monster black holes may also be the hungriest. That is because supermassive black holes at the centers of galaxies in cosmic deserts of the universe, where neighbors are rare and stellar, nourishment is scarce, still manage to munch on material more often than their counterparts in more crowded areas of the galaxy. In the past decade, astronomers have debated whether galaxy mergers, similar to the one underway between the Milky Way and the Andromeda Galaxy, are the main triggers that strip material from galaxies and funnel it to colossal black holes at their centers. New observations, which found over 20,000 hungry black holes in lonely slices of the universe known as cosmic voids, show that these invisible beasts snack more often when there are fewer interacting neighbors to interrupt them. And according to Anka Konstantin, an astrophysics professor at Virginia's James Madison University who co-led the study, these findings challenge our current understanding of how galaxies evolve. Cosmic voids are essentially 3D bubbles of space, some of which stretch over 500 million light-years across and contain just a handful of galaxies, if any at all. Also called the universe's wastelands, cosmic voids are thought to make up half of our universe, and together host 20% of its galaxy population. There is growing evidence that the Milky Way, too, is contained in a spherical void, whose radius is at least 1 billion light-years across, which is 7 times larger than an average cosmic void. The remaining 80% of galaxies of the universe are birthed in more crowded regions, where anywhere between 50 to 1,000 huddle in galaxy clusters, researchers say. The 80% of galaxies that live in the more populated corners of the universe are huddled close enough to interact gravitationally with each other and eventually merge. During this process, galaxies strip matter from one another, which in turn feeds the supermassive black holes at their centers. However, precisely how the material gets directed into the black hole, such that it begins snacking or munching on that surrounding matter, has been heavily debated, said Anish Aradhe, co-led the study. The merger theory lacks a robust explanation of how black holes grow in galaxies that are friendless in their cosmic neighborhood, and thus do not interact with each other, a process thought to be necessary to make stellar food available. So to learn more about how exactly black holes start feeding, Aradhe and his team studied hungry, supermassive black holes in the loneliest galaxies in places of the sky called cosmic voids. In the words of researchers, galaxies are more able to channel that fuel towards centers of supermassive black holes if they don't have to compete for that fuel with their neighbors through interactions and stripping and other processes. Using 8 years of data collected by NASA's Wide Field Infrared Survey Explorer or WISE sky mapping telescope, Aradhe's team studied how the brightness of about 290,000 galaxies changed over time and discovered over 20,000 actively feeding black holes that were hidden in previous searches. Past surveys on void galaxies focused their searches on optical or mid-infrared wavelengths, the latter of which relied on detected light to categorize the activity within galaxies. The bluer the light, the more intense the star formation, while red light suggests emissions from a hungry black hole feeding on material. However, void galaxies host lots of star formation and thus emit bluer light emissions, which drown out the light from feeding black holes within them, thus masking their presence, Aradhe said, which explains why past studies missed them. Instead, his team studied telltale fluctuations in brightness of infrared light over time that betrayed the presence of feeding black holes, whose activity turned out to be more common in small or mid-sized galaxies than large ones, the team found. The bottom line, the smaller galaxies seem to snack more effectively, if you will, when they are left alone and they don't interact with their neighbors. In another remarkable study, astronomers have just discovered 3 ancient stars on the run in the outskirts of the Milky Way galaxy, racing the wrong way at hundreds of thousands of miles per hour. Despite being sprightly for their age, the 3 stars are so old that they date back to the formation of the first galaxies. That's between 1 and 2 billion years after the Big Bang. Researchers from the Massachusetts Institute of Technology, or MIT, found these stars in the Milky Way's halo, a diffuse cloud made of stars, gas, and dust that envelopes our entire galaxy. The team has named the stellar bodies, which have ages between 13 billion and 12 billion years old, Small Accreted Stellar System, or SAS, stars. The name indicates that each of these stars formed in its own small, primitive galaxy that was later cannibalized by our Milky Way. The researchers believe there may be more ancient star stragglers existing at the edges of the solar system, forming a sort of fossil record that details how our galaxy grew by consuming others and adopting their stars. Such stars could also be used as analogs to study the 13.8 billion-year-old universe's earliest stars and galaxies. As team member and MIT professor of physics, Anna Frebel said in a statement, "These oldest stars should definitely be there, given what we know of galaxy formation. They are part of our cosmic family tree, and we now have a new way to find them. Discovering more SAS stars would mean more analogs of stars in so-called ultra-faint dwarf galaxies, which are the universe's oldest surviving galaxies. Though these galaxies remain intact, they are too distant and faint to be investigated in detail. Ripped from similar primordial galaxies and absorbed into the Milky Way, SAS stars are, therefore, a more accessible avenue to understanding how some of those very early galaxies evolved. The search for ancient stars at the edge of the Milky Way began in 2022 as part of Freeble's new Observational Stellar Archaeology course. During these sessions, the MIT researcher detailed methods of investigating older stars and discussed how these methods could be applied to unstudied stars to determine their origins. As Hilary Andals, part of Freeble's lab at MIT's Kavli Institute for Astrophysics and Space Research, said in the statement, "While most of our classes are taught from the ground up, this class immediately put us at the frontier of research in astrophysics." Fredel's students scoured through years of data collected using the 6.5-meter Magellan Clay telescope at Las Campanas Observatory to find stars of interest, particularly those with low concentrations of elements heavier than hydrogen and helium. When the first stars formed, the universe was filled with mainly hydrogen, a little helium, and only a smattering of heavier elements, which astronomers call metals. As these stars lived, they forged metals in the cores, eventually exploding and dispersing elements. Those elements then become the building blocks of the next generation of stars. That means the first stars should have metal-poor compositions compared to later stars that have been enriched by previous stellar contributions to the universe's heavy element manifest. To identify ancient stars lurking in the Milky Way, students under Freeble's tutelage focused particularly on stars lacking strontium and barium. This led them to 3 stars that had been observed by the Magellan telescope in 2013 and 2014. They were bodies that had not been very deeply investigated by astronomers. Not only did the 3 stars highlighted by the team lack strontium and barium, but the object's iron content was also quite low in comparison to more modern stars, like our 4.6 billion-year-old star, the Sun. In fact, for one of the stars, the ratio of iron to helium is 10,000 times smaller than the ratio of the same elements for the Sun. And sure enough, the chemical composition of the stars not only revealed them to be between 12 billion and 13 billion years old, but it also showed a remarkable similarity to the chemical composition of ancient ultra-faint dwarf galaxies. Furthermore, to discover how these ancient stars came to be part of our galaxy, the researchers looked at their orbits and paths across the sky. This revealed the stars to be in 3 different locations of the Milky Way's halo and sit around 30,000 light-years from Earth. The origin of the stars as part of galaxies gobbled up by the Milky Way was revealed not just by their metal-poor compositions, but also by the fact that they orbit in a different direction to the Milky Way's main disk and most of its halo. The stars also exhibited random angles and odd trajectories that have persisted for billions of years. In investigating this retrograde motion, the team discovered another 65 stars showing the same pattern. Those stars also had low strontium and barium contents, but strikingly, they had something else in common with the SAS stars, too. They're on the run. Interestingly, they're all quite fast, hundreds of kilometers per second, going the wrong way, Freeble explained. We don't know why that's the case, but it was the piece to the puzzle that we needed, and that I didn't quite anticipate when we started. There are around 400 billion stars in the Milky Way, and Freeble and colleagues will now search for more SAS stars among them. They'll do this by looking for metal-poor stellar compositions, then checking if the selected subjects have orbits that don't match galactic flow. Additionally, Freeble's Observational Stellar Archaeology course will be back next year, allowing more students to learn about her intriguing methodology. These results, in a way, are its validation. As Freeble concluded, It's been awesome to work with 3 women undergrads. That's a first for me. It's really an example of the MIT way. We do. And whoever says, I want to participate, they can do that, and good things happen. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.